folks, Mrs. White here. Today we're going to start off by looking at section 5.4, which is going to be graphing square root functions. Hopefully your sit and begin today, even though it's not really a sit and begin, is going to be to make sure you check PowerSchool. Your quiz grades should be up at this point if you submitted everything on time last week. What I'm going to do is I'm going to be reporting out your actual percentage grade that you earned on that. But again, things are pass fail right now, so it's not actually going to affect your year one or your quarter four grade. So you'll see a percentage tied in there, but hopefully your quarter four grade will just kind of be empty looking right now. And that way, at the end of the quarter, we can take all those grades and average them and see where you are as far as pass fail. So, food for thought, check out your quiz grade, see how you did. If you have any questions about what you got wrong, feel free to pop me an email and I can give you back some of that feedback. I am not just going to send everyone out a copy of their quiz until I have everything submitted from all the classes. So, once I have everything turned in from each of my honors classes, I'm happy to get that back out to you. Okay? So today, we're going to look at graphing the square root function. We're going to start off our discussion with what is the parent function? What's the most simple square root function actually look like? How can we, looking at the function, determine the domain and range? Okay, because when we think about inverses and compositions, domain and range are important. And how can we get that without actually having to graph it? Secondly, how do we go about graphing every single square root function given specific translations? And these translations and dilations are all, and reflections, excuse me, are all exactly the same as what they were for absolute value functions. So what's really nice today is that when we talk about the graphing piece, it should feel very familiar to you. We just have to apply it to a different parent function, okay? And then lastly, we're going to look at, well, we're graphing square root functions. Why the heck are we doing that? How is it tied into inverses? So we'll take a look at that. You do have homework tonight. I want you to do all of 4 through 12, page 341. That's going to have you look at doing a bunch of graphing. So if you have some way that you want to do that, you're welcome to do it on scrap paper. But if you want to try to do it digitally and you have the means, that's fine also. I do want you to be thinking about listing out what the actual translations and dilations and reflections are. That way, as you're graphing them, you're also solidifying your understanding and your review of that also. Okay, so think about what are the shifts, and we're going to try to avoid making a bunch of tables today if we can. Okay? So if you need to, pause it, double check your quiz grade. If you have any questions, pop me an email, and otherwise, let's just get going. So we're going to start off by talking about the parent function of a square root graph. So f of x is like our y equals the square root of x. This is the most simple square root function we can ever have, right? Like the most simple line would be y equals x. The most simple parabola would be y equals x squared. So we can say we have y equals the square root of x is our most simplified one here. Okay, so what we're going to do is we'll make a table with this one. We'll graph it up and kind of determine our domain and range from that. And then we'll talk about shortcuts from the equation and how we can use those to help us determine domain and range without having to graph it. So let's see, we go negative 10 and positive 10 here. Let's start out with maybe negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and then we'll save this one for the end, okay? So what I'm doing is I'm going to plug in negative 4 right here and for x. So my equation is going to be essentially y equals the square root of negative 4. Now I hope right now you're like, Mrs. White, you cannot have the square root of a negative. It's going to be imaginary. We are not graphing on the imaginary plane. These are only real numbers. If our solution is going to be imaginary, it's just not going to happen, okay? So think about this. What's the square root of negative 3 going to be? Well, square root of a negative can't have it. Square root of negative 2 can't exist. Square root of negative 1 is by definition I, but I is not graphable on this plane. Okay? So now we're down here. Square root of 0. So what number times itself equals 0? Well, the answer is 0. So our first point is going to be here at 0, 0. Next, we have square root of 1. So what times itself equals 1? And it's going to be 1. Square root of 2. Now, the square root of 2 is not a nice number, okay? So maybe we'll skip that for a second. We'll come back to it. This is an irrational number, right? We've talked about rational, irrational, imaginary, and complex, and real. This is going to be a real number, but it's going to be a hot mess decimal, Okay, so we'll hold off on that for a second. Square root of 3 is the same thing, right? That's not easy to know just by looking at it. We'd have to use a calculator, so we're going to pause on that one. But square root of 4 we can totally do. Okay, what times itself equals 4? The answer is 2. So I'm going to go over 4 and up 2. So right now we're seeing this kind of shape right here. Okay, and what we noticed is it's easiest to plug in perfect squares into our square root sign. So there's actually one more we could graph here nicely. What other number could we have under here that's going to give us a nice number that we could graph? It's going to be 9, okay? So we could plug in 9 and get square root of 9 equals 3. I'm going to go over 9 and up 3. So you can see this is not an up 1, forwards 1, up 1, forwards 1. It's not even up 1, forwards 2, up forwards 3. It's like a very specific pattern, and that pattern is the square root function, okay? So it's going to start at 0, 0. It goes up 1, it goes over 1, up 1, and then it goes over 3, up 1. And then it's going to go over 1, 2, 3, 4, well, I miscounted, 1, 2, 3, 4, 5, up 1. Okay, so it's not necessarily like a super easy pattern for you. It's dictated by what works well for our perfect squares in there. Now let's take a second. I'll pull up my calculator and do it on my phone. And I'm going to do the square root of 2 really quick so we can just get that number in there. So square root of 2 is 1.41. I'm going to do square root of 3, and that gives me 1.73. So I could go over over to 2, up 1.4, a little bit less than half. Go over to 3 to 1.7, right about there. And you could see, okay, yeah, that's going to start lining up nicely. And I know my curve that I drew isn't perfect, but you can imagine what this piece would look like here. Okay? So this is interesting because both our domain and our range are limited by this function. So our domain, we are going to look at what is our minimum, our maximum, and breaks. There are no breaks in this graph. So we're thinking as far as our x is concerned, what's the smallest number that our x could equal? It's 0. What's the highest number our x could equal? Well, it can equal 10. It could come out here. In fact, there's an arrow, right? So it could come out this way forever. So really, our domain is only limited by a minimum of 0. So we would write domain colon curly bracket, all the values of x such that we have an x, we have a 0. 0 is our minimum, so our alligator would never eat it, and it would equal it because there's no open dot there. Okay. We also could write this in what we call interval notation. Excuse me for a second. Okay, sorry about that. In interval notation, you use parentheses and you use brackets, and you only put 2 numbers in it. Okay, and so I'll talk you through how to do it here, and I'll put them on the next couple examples. Mrs. Boyce will spend some time teaching you interval notation in pre-calculus, but I thought it'd kind of be a nice time for you to see it now. So looking at this problem, we are going to use the square brackets every time that it includes a number. So if it's like a closed dot, so if it would be like these, or if it's inclusive is the words we want to be thinking about. And we would use parentheses if it's something that you can never actually reach. So it would be greater than, less than. You could think of it being something that's exclusive. You also would use this if you're using infinity, like if there's no maximum, okay? You would use the parentheses because you're actually never going to equal infinity. You're just going to try to get there. So it always is going to kind of look like a coordinate pair where you have your minimum here and your maximum here. So we said we did have a minimum and it was 0, right? And we also said that our function could equal 0 since it's a closed dot. So we would put a square bracket there. So this means including 0. It's going to go all the way to, well, there's no maximum, so it's working its way out to positive infinity. Are you ever going to be able to reach positive infinity? No, so you just put parentheses just like that. Okay, and some notation might have the plus for positive infinity. Moving forward, we'll put the plus and the minus just so it's giving us kind of direction. Okay, so these two things mean the same thing. This is what we call set builder notation. This is interval notation. I don't care which one you do. Some people like this more, some people like this more. Interval notation gets kind of yucky when you have breaks. So that's why we're looking at it now that we're dealing with continuous functions, right? Versus ones that have breaks. So let's talk about our range now. Our range has to do with our y's. So we do have a minimum y, right? Our graph does not exist below here. And you might feel like, well, don't we have a maximum, Mrs. White? This kind of looks like it's leveling off. It's not going to actually ever be horizontal, because if you think about it, right, we could plug in the number 25 here, and we get square root of 25 is 5. We could plug in the number 100 here, and square root of 100 is 10, and so we'd have 100 comma 10. So it's going to just be going up very, very slowly once you get out this way, okay? It's the opposite of a square function, right, which increases very quickly, right, on one side of that parabola. This one kind of, boop, just kind of starts mellowing out. So there actually is no maximum. This is going to continue out, but also up very gradually forever. So if we're dealing with our range, we're going to imagine set builder, all the values of y such that y is limited by 0 right here. That was our minimum. So it's going to look a little something, something like this. If we want to put it in interval notation, our minimum was 0. It could equal 0. So we do a closed bracket, not a closed bracket, a square bracket. And then there's no maximum on our y, so we're going out to positive infinity. You can never actually get to positive infinity, so we put a parentheses. Okay? So this is our general parent function. The idea that I want you to kind of stick in your head is that it's going to start at 0, 0. Okay, so if we shift it up, down, left, right, we're going to think about this being what moves up, down, left, right. Then from that point, you want to plug in perfect squares. And it might not be perfect squares that you think about. It's going to be, you want underneath your radicand, so you want this piece here, whatever's underneath your root, you want this chunk to become a perfect square. So what would we plug in for x to make it a perfect square? So we can get the points like 0, 0, 1, 1, over 2, or over 4 up 2, over 9 up 3, right? We want those perfect square ones so that we can get the general shape. You have to graph at least 3 points for it to be considered graphed, okay? Because if you only do 2 points, look, boom, boom, 2 points, it could be a line. At 3 points, you start getting that general shape of the actual curve. So, graphing this is a lot of work, especially if all you're asked to do is find the domain and find the range. So there's actually a quicker way for you to determine domain and range just from the function itself. So let's take a look here. We have the square root of x plus 4, so our radicand was going to be x plus 4, and we're square rooting it, and this is our y. So they don't say graph it, they just say identify it, okay? Just identify your domain and range. So one thing that's interesting here is that your domain, okay, so we'll do domain first. Your domain is always going to only include the values for which this is positive, right? If we have a negative underneath here, we're automatically going to be in imaginary numbers, and that's not going to work. So the way that we can kind of determine our domain is we're going to take our radicand, so we're going to take our inside of our root sign, our x plus 4, and if that number has to be positive, we can't say equals positive. We can say that it needs to be greater than or equal to 0. Now that's going to give us all of the x values, okay, that are going to be resulting in positive numbers. If they're greater than or equal to 0, they have to be positive, okay? So this is what you're going to do every time for domain. You're going to take your radicand and you're going to say, okay, that radicand must be greater than or equal to 0, and then I'd minus 4 minus 4, and I get that my x must be greater than or equal to negative 4. Well, that legitimately is going to be my domain, okay? My x's must be bigger than that. So any value that's bigger than negative 4 or equal to it is going to work. So if I was writing the domain itself, I could do all the values of x such that x is going to be greater than or equal to negative 4. Negative 4, if x is bigger than it, that means this is a minimum, right? So I could put negative 4 inclusive, right? Because it would be filled in dot equal to, all the way to positive infinity would be my domain for this graph. Now to do the range, there's something similar, okay? We're going to take whatever we found for our domain, the value here. Let's see if I can switch up the colors a little bit. You're going to take whatever value you got here, and you're going to plug that in here, and that's going to give you your limitations for your range, okay? So we're going to figure out f, sorry, I'll label this, we're doing our range. We're going to do f of negative 4, and that means I'm going to take out my x and replace it with negative 4. So I have the square root of negative 4 plus 4. And hopefully right now you're like, oh, that's just the square root of 0, excuse me, and the square root of 0 is just equal to 0. Okay? So what that means is that 0 is going to be our minimum value also, since we plugged in a minimum value for our x, right? This was a min, so we're calculating the min for our y, and it's going to be at 0. So if we were to do set builder, we would do all the y values such that y is going to be greater than or equal to 0. Remember, if 0 is a minimum, an alligator's never going to eat it. If I were to do it in interval notation, 0 is the minimum. It could equal it. It's going to head out for a maximum. There is none. There was none here, so there's none here. And we're never going to hit that positive infinity. Either of those two are fine with me. So what I want you to do right now is take a second. Without graphing, I want you to give a go to these two problems below. I will put up my work for each of them, and then I'll talk you through them. But feel free to pause the video if you need to, because I'm going to speed up my work. All right, so for our first one here, if you take a look, our domain, I took my radicand. I said it has to be positive, so it has to be greater than or equal to 0. I solved for it. That became my inequality in set builder. X must be greater than or equal to 3. Then I put it in interval notation. If x has to be bigger than 3, then 3 would be a minimum. It can equal it, and it's going to continue out to positive infinity. The range, I took this 3 value I calculated, I plugged that in to find my range's minimum. I put 3 minus 3, which is 0, and square root of 0 is 0. So 0 became my minimum for my y. I wrote it in set builder. And then, since 0 was the minimum and it could equal it, I put a square bracket, comma. This should be positive infinity is my maximum. Okay. I'll give a go on this one, which is going to be a little bit different because I'm adding on the outside now, so it's going to influence my range piece. Again, for the domain, I only care about the radicand. All right, so let's talk through this problem. I took just my radicand, okay, and I said that the inside, in order for it to be a real number, has to be greater than or equal to 0. So I minus 6 minus 6. That means my x, in order for us to have positive numbers under here, has to be greater than or equal to negative 6. That happens to be my domain. Again, it could equal negative 6, and it's going to head out to positive infinity with no maximum. My range, I took that negative 6 I found for my minimum, and I was going to try to find my minimum for my y. So I'm going to take that negative 6, plug it in. It gives me a 0 under here, okay? But because in my original function I have a plus 2, the whole thing ends up with a plus 2. So this positive 2 becomes my new minimum for my y. So my y's must be greater than or equal to 2. So 2 is my minimum, including the number 2. And it's heading out to positive infinity, but will never actually equal positive infinity. Okay? Again, you only have to do set builder or interval notation, whichever one you like is fine. I will, in my handmade keys, accept both. I'm not exactly sure what the book's going to expect from you. So when you check out the key for your homework, be willing to look for both formats. Okay? So let's talk about general patterns in the graph now. So we talked about general patterns in our domain and range. So let's talk about how does that impact our actual graph. So here is the general form of a square root function, and I know it looks a mess a little bit, okay? But what this is going to do is it's going to tell us all the different types of translations we can have, okay? So I'd write this down. F of x equals a times the square root of x minus h plus k. And this should look familiar. It should look similar a little bit to our vertex form, which looks similar to our absolute value form, okay, when it has this like h and k idea. So any type of movement in our h function, right here, or not h function, h value, is going to be a horizontal shift, okay? So that's going to be a shift left to right, and because it's a minus h, folks, it's going to look opposite of what you would normally think. Over here, the plus k is on the outside. That is going to be a vertical shift, a vertical translation. It's going to be up and down. Okay, sorry about the pen. A is going to change the steepness of your actual curve, okay? So that's going to be what causes a dilation, which if you think back, every time you multiply by something, that's the type of change it makes anyways, okay? So that is going to be some sort of dilation. It also could change the orientation and be a reflection, okay? So we'll talk about each of those pieces and parts in a little table on the next slide. But I want you to have this as the general form, a times the square root of x minus h plus k, where k is going to be a shift up or down. H is going to be a horizontal shift left or right, and it's going to, because it's a subtract, look opposite of what you see here. And then your a value is either going to make it steeper or flatter. And if that a is negative, it's going to potentially be a reflection. Okay? Either over the x-axis, or we are going to see eventually something over the y-axis also. So let's talk about a quick review. Since a lot of these rules are very similar to what we learned in the past, I thought it'd be helpful to kind of see this table and be able to just plug and play stuff into it so you know what the shifts are. So feel free to make this in your notes if you want to use this to help you memorize things, great. If you just want to remember a times the square root of x minus h plus k, that's fine too. So if you're adding inside, which means you're doing something like this, square root of x plus 3, okay? If you're adding on the inside of your radicand, on the inside of your root sign, this is going to be the opposite of what you think, and because it's happening to the x, it's going to be a horizontal shift. So on the x, instead of, you might think it's going to go forwards 3, it's actually going to go to the left. So when you add inside, it's a shift to the left, and this one specifically would be to the left 3 spaces. So instead of starting at 0, 0, it's going to go to the left 1, 2, 3. It's going to start there, and then it would go up 1, forwards 1, up 1, forwards 3. Which, if you don't remember that pattern, that's fine. From there, you would just make a very, very small table. So if we're going to subtract inside, so let's say we're doing the square root of x minus 3. Okay, and that minus 3 is on the inside. It's part of your radicand, okay? Your h value here is technically 3, right? Because we're minusing h. So that means we're actually going to shift it to the right. And if you just want to remember that's kind of the opposite of what it looks like, that's fine. This is going to be, again, a shift to the right, 3. So when you add on the inside, it's left. It's the opposite of what you think. When you subtract on the inside, it's going to be a shift to the right. Now, when we add or subtract on the outside, so if we add on the outside, or if we have the square root of x and we subtract on the outside, this is going to be a vertical translation. This is your k value, and it's going to be exactly what it looks like. So if you're adding on the outside, that's going to be a shift up. If you're subtracting on the outside, it's going to be a shift down. And hopefully that's very familiar to what we were doing with square roots. H and K translations aren't that bad at all, okay? Sometimes it's getting the follow-up points after you determine where that, parent function normally starts right here at 0, 0. Once you figure out the up, down, left, right, that's pretty quick and easy by just looking at these if you have them memorized, okay? Now here's where things get a little bit funky. If you end up multiplying on the inside by a positive, so let's say you have the square root of 2x, okay? What that's going to do is it's going to be a dilation. It's going to change the steepness. Okay? Not steepness. There we go. Sorry about that. Okay. So if we think about that, and we'll do a couple examples moving forward where this happens, you're taking your x and you're doubling it every time. So if we were to make a little table for this, so let's maybe do that below here. And I want to plug in, a couple x values. I see if I plugged in any negatives for x, it's not going to work here, right? I'll get an I value. So I'm going to start off with 0. And then I'm going to choose 2, and we'll tell you why I'm going to do that in a second. And then I'm going to choose 4.5. I know that seems pretty random, but you'll see why in a second, okay? And then I'm going to get out my y. So if I plug in a 0 here, 0 times 2 is going to be 0. Square root of 0 is 0. I chose 2 because watch what happens. I'm going to plug a 2 in here. 2 times 2 is 4. Square root of 4 is 2. So our normal, if we think back to our parent function, okay, it normally starts at 0, 0, and then it goes over 1, up 1. Well, if we look at what happened here, okay, It still starts at 0, 0. It didn't move left, right, up, or down, okay, because there's no adding or subtracting. But our steepness went from being up 1, forwards 1 to up 2, forwards 2. Okay, or excuse me, our x being 2, so we'd go over 2 and then up 2. Next, I have this 4.5. So 4.5 times 2 is 9, and square root of 9 is 3. I chose 4.5 because I wanted this inside to equal 9, and I knew 2 times 4.5 is going to give me the 9. So now, instead of going over 4 boxes, okay, and up 2, I'm going to go over 4.5 boxes and up 3. So this is actually going to make it a little bit steeper, but it's not that everything is doubled, okay? I didn't go over 4 boxes, right? I didn't go over 8 boxes and then go up 4. That's not how it works, okay? It's a little bit more specific than that because the square root happens after you double it. All right. However, if you multiply it on the outside by a positive, it's literally just going to double whatever you had going on the inside there. So 2 times the square root of x is going to affect the steepness. And again, here I would just plug in 0, and I would get 2 times the square root of 0, which is 0. So 2 times 0 is 0. I'd plug in 1, I'd plug in 4, I could plug in 9. I'd plug in all my perfect squares here to get that table value. Now, one thing that I didn't mention in either of these, I said that it makes it steeper because we were dealing with 2. If you're dealing with a number that you're multiplying by, and it's greater than 0, but it's less than 1, so it's a decimal between 0 and 1, then it's actually going to make your graph appear more flat. Okay? And that's the same if you're multiplying on the outside. So if you have a number and it's bigger than 0, but it's less than 1, so 3/4, 5/8, any of those types of fractiony things, okay, that's going to make it more flat. So here's where we start having to think about it, okay? If we are multiplying, we'll start with the outside. On the outside by a negative, this is going to be a reflection. And it specifically is going to be a reflection over the x-axis. So here, our normal graph looks like this, right? It's going to look like this, okay? That's a reflection over the x. If you're multiplying the inside by a negative, you need to make sure you factor that negative out. And that's also a reflection. It's a little bit less common for what we're working with in this chapter, but it's good for you to know. Oh my gosh, my pen. It's going to be a reflection, but it's going to be a reflection over the y-axis. So if our parent function looks like this, right, our other one is going to look like this. That's what a reflection over the y would look like. Okay, it's going to look like it's backwards. Here it looks like it's upside down. So if you wanted to write backwards here and you want to write upside down here, that would kind of give you an inclination about what to do. So honestly, folks, I generally use these 4 shortcuts all the time. And then I think about if I'm multiplying by a negative. But when it comes to multiplying here and here on the outside or the inside, our steps moving forward are to make a table. Because we're dealing with square roots, we can't just kind of say it went up by whatever. It didn't double every single time necessarily. It could be a little bit more involved than that. So we'll practice that. We'll do some easier graphs and some trickier graphs right now. So let's take a look at these 4. We're going to pause on doing domain and range right now just to keep this video at a reasonable time. We're just going to talk about the graphing, okay? I do want you to do domain and range in your homework. So here I see I'm subtracting on the inside and I'm adding on the outside. So there's 2 things going on to this parent function. Now I am going to draw the parent function really quickly. It starts at 0, 0, it goes up 1, forwards 1, it goes up 1, forwards 3. Okay, so this is what I'm thinking for my parent function. Now I'm going to graph this one. When I subtract on the inside, if it's happening on the inside, it's happening to the x, so it's a horizontal shift, and it's going to be the opposite of what I think. So instead of going to the left 2, it's actually going to go to the right 2. And then this plus 5 on the outside is like our b value, right? It's a shift up or down, and it's going to be exactly what it looks like. It's going to go up 5. And now nothing is being multiplied here, so the steepness doesn't change. So instead of starting at 0, 0, I'm going to go to the right, 1, 2. I'm going to go up, 1, 2, 3, 4, 5. Put a dot right there. Since the steepness didn't change, I'm going to go up 1, forwards 1, up 1, forwards 3. And my graph is going to go like this. Sorry about my pen. Okay, just a quick little sketch. It cannot exist over here because it's going to be imaginary, okay? It cannot exist below here because those solutions would just not work. They're not going to exist. Let's take a look at B, okay? So I'll start off with my parent function, 0, 0, up 1, forwards 1, up 1, forwards 3. Then I'm going to think, what are the shifts that are happening here? Well, I'm adding on the inside. I'm subtracting on the outside. So I got two things there. I'm multiplying, and I'm multiplying by a negative. Now, if you are multiplying by anything, your last step is going to be to make your XY chart. And then just make sure you have 3 points, and that's starting with your lowest value. Okay? So, and by lowest value, I mean where your origin could be. And that's what we're going to get from our left, right, up, down right now. Okay? So inside my radicand is going to happen to the x. It's the opposite of what I think, so I'm actually going to go to the left 3 towards the negatives. This is going to be exactly what it looks like. It's going to be down 1. So I'm going to go left 3, 1, 2, 3, down 1. There's my origin. So my first coordinate pair is negative 3, negative 1. Okay, if I plug in a negative 3 plus 3 is 0. 0 times negative 2 is 0. Minus 1 is negative 1. Now, to get my other points here, I want to figure out my, perfect squares that I could plug into here. So in my head, I'm thinking 0, I'm thinking 1, I'm thinking 4, and I'm thinking 9. So negative 3 gave me the 0 here, right? I wanted x plus 3 to equal 0, and that's how I got negative 3. Well, now I'm going to do the same thing, and you can do it with mental math, or you can actually write it down. I'm going to take my radicand, x plus 3, and I want that inside to equal 1 because that's my next smallest perfect square. So I'd minus 3 minus 3. That means I'm going to plug in negative 2. So watch what happens. When I plug in negative 2 here, I get negative 2 plus 3, which is 1. The square root of 1 is 1. 1 times negative 2 is negative 2. Go backwards one more, negative 3. Next one, and I only need 3 points. We could do 4 if we want to, but I'm going to say, all right, I want my inside to equal 4. So I currently have x plus 3. To get it to be a 4, well, x would just have to be positive 1. So 1 plus 3 is 4. Square root of 4, and that's why I'm choosing this, folks, so I can use mental math, okay? Square root of 4 is 2. 2 times negative 2 is negative 4. Minus 1 more, negative 5. So let's look at what happens. It starts here. Okay, that's my negative 3, negative 1. Then I'm going to go negative 2, negative 1, 2, 3. So it's clearly getting steeper, right? It's going to come out this way. And it's reflected over my x, which is what happens when we have a negative on the outside also. Okay? So then I'm going to go over to positive 1 and down. There's 3, 4, 5. And I'm going to start with my origin and continue out this way. So you can see that it got steeper because we multiplied by a number greater than 1. Okay? The negative, all right, the negative here meant that it was going to be a reflection over the x. And I moved it left 3 and down 1. I want you folks to take a second on these two. I'm going to write out each of my bullets and graph them and talk you through it in a minute. All right, folks, so I noticed that I was adding on the inside, which was a shift left 4. Then I was multiplying. So when I'm multiplying, I'm going to make an XY chart. And I looked at just my radicand and I said, okay, I want this to equal 0. Okay. I want this inside to equal 1, and then I want this inside to equal 4. And I did a lot of that with mental math just to try to not write everything down since this pad doesn't work great. So if it's going to equal 0, this has to be negative 4. So I put a negative 4 as my first x. Then if I wanted the inside to equal 1, negative 3, if I plug it in here, will give me my positive 1. And then lastly, if I want it to be my next perfect square, which is 4, I'd plug in a 0 for x, and that will give me 4. So once I did each of those, I actually plugged it in and PEMDASed it. It might look like I didn't really do anything, but I did it again with mental math. If I take negative 4 and plug it in here, negative 4 plus 4 is 0. Square root of 0 is 0. 0 times 2 is 0. So I'm going to go negative 4, 0. Which honestly, folks, that's my left 4, right? That's where it starts. Now I've got my negative 3. So negative 3 plus 4 is positive 1. Square root of 1 is 1. 1 times 2 is 2. So that's where I got this 2. So negative 3 up 2. You can see it's getting steeper. Then I'm going to plug in 0. 0 plus 4. And make sure you take your time on this, folks. 0 plus 4 is 4. Square root of 4 is 2, and 2 times 2 is 4. So I'm going to go over to 0 and up to 4. Biggest mistake people make, folks, is that you get so used to like getting a 0 and square root of 0 is 0, and then you get a 1 in here and square root of 1 is 1, that when you get 4 in here, people forget to square root it and they would accidentally put 8. So if you had an 8 there, if you paused the video and kind of did this on your own, that's the mistake you made. You forgot to probably square root that 4. So there's our graph. I'm going to go through and put some markings for this one, but I see I'm multiplying, so I'm going to have to do a table again anyways. Six minus 5 is 1. Square root of 1 is 1. 1 times 1/4 is 1/4. Plus 3 is 3 1/4. Last one is 9. So 9 minus 5 is 4. Square root of 4 is 2. 2 times 1/4 is 2/4, which is like 1/2. And 1/2 plus 3 is 3 1/2. So it's going to start at 5, 3. So over 5, up 3. I'm going to go over 6, up 3 1/4. And then I'm going to go over to 9 and up 3 1/2. So you can see this is very, very, very flat now. And it'd have a little arrow coming out this way. So how is this related to what we've been doing so far in chapter 5? Well, square roots is going to be one of the graphs we're just going to have to practice and know how to do, and that's why you're going to see a lot of problems involving graphing it and doing domain and range for homework. But it also is related to our x squared function, and you maybe noticed this in section 5.3. So find the inverse of f of x equals x squared. So I thought we could take a second and review how do we find inverses. But we're going to limit our domain to x values that are only greater than 1. So when we go to graph it, okay, we're going to graph f of x equals x squared, and then we're going to do the inverse of f of x on the same plane. We're only going to graph where x is greater than or equal to 0. So let's start by finding our inverse. To find the inverse, we flip-flop the x and the y. So instead of y equals x squared, it's going to be x equals y squared. Then to get our y alone and positive, we're going to square root it, and we're going to end up with y equals the square root of x. Now, we know a little bit about this function. This is our parent function, okay? But if we wanted to look for where our x values are greater than or equal to 0, we would start by plugging in 0 here. And square root of 0 is 0, so our first point, 0, 0. Again, we could just make an xy chart if you wanted to. We could plug in 1, so square root of 1 is 1. We could plug in 2, we could plug in 3, but what we really want to plug in here is perfect squares, so we could plug in 4, we could plug in 9. When we plug in 4 and square root it, we get 2. When we plug in 9 and square root it, we get 3. So our next 2 points are going to be 4, 2 and 9, 3. So here is our square root function. Okay, and if you look, this does have a limited domain naturally, right? X must be greater than or equal to 0. Well, that's where this function can exist anyways, okay? Now, so we just graphed this in red. So let's graph our original function. Now we're dealing with a parabola here. It starts at 0, 0 for this parent function, and it goes 1, 1, 1, 1 here, and then it's going to just kind of go up. Okay, it's going to be a parabola that kind of hits and goes up like this. But if you think about it, knowing what we know about inverses is every point should be reflected around the line y equals x. So right on this purple line should be where it's reflected. So if you think about it that way, this is on that line, this is on that line, this one is 2 away here, so we could go 2 away here. This, okay, is 1, 2, 3, 4, 5, 6 away. So I could go 1, 2, 3, 4, 5, 6 away right there. And instead of reflecting these over the axis, I don't even want to even include this one, right? I only want to have where x is greater than or equal to 0. So you can see right here, when we limit the domain of our parabola, that's where we end up getting our square root function here. Now you might say, Mrs. White, why don't we just have the whole parabola, right? We would have the other part coming up like this. Well, if we reflected it here, then we'd end up with this piece that goes something like that. And now if we were to try to do our vertical line test on this function, everywhere it would double up and it would not be a function, okay? And so that's why we really only use our principal root when we're graphing square roots, because one, we need it to be a function, and two, without that, when we have that negative piece with it, it's going to diminish that, okay? So your task for tonight / tomorrow / before the next information is released to you, okay, is going to be to do ebook, again, 4 through 12, all of them, page 341. It's going to involve some graphing. So please make sure you're writing out the list of ways that it's going to be changed. And when you make your little XY chart, which you should be making if you're multiplying, okay, you should be picking X values that when you take the radicand, which is the section underneath your root sign, okay, when you take this, you should be setting the inside equal to 0, the inside equal to 1, and the inside equal to 4, because those are the smallest perfect squares, and they're going to give you the nicest points to graph. You could pick random numbers, okay, but then you're going to be graphing decimals. If you choose x's that result from this, then that will be easier, okay? If you have any questions, feel free to show up for my office hours, not tomorrow, but the day after, so on Wednesday from 1 to 2. I hope to see you there, especially if you do have questions, folks. Don't email me with them. Show up to office hours, okay? Thank you. Have a good one.